Good morning to one and all. My name is Sheikh Muhammad Iqbal. Today I am going to represent a seminar in DLD Digital Logic Design. Today I am going to give a seminar in the topic of error detection in codes and error correction in the codes. So let's dive into my seminar. First of all, we're gonna discuss about the error detection codes. In a 4-bit binary code, the occurrence of a single error in one of the binary digits may result in another incorrect but valid word. If a code possesses the property that the occurrence of any single error transforms a valid code word into an invalid code word, it is said to be a single error detecting code. The error detection is accomplished by a parity check. The basic idea in the parity check is to add an extra digit to each code of a given code so as to make the number of ones in each code word either odd or even. For example, if we send a code to the receiver, then he may get correct code or wrong code. We can detect this error code by using an extra bit named as parity bit. This parity bit is of two types. We can follow even parity or odd parity. For even parity, this bit is set to 1 or 0 such that the number of ones bit is in entire word including the parity bit should be even. That means we should count that all the ones in must be in odd number of ones in odd parity. For even parity, the set of ones or zeros that the number of ones entire word including the parity bit should be even for even parity. Let us take some examples using BCD code. A BCD code is a 4-digit code. BCD is code. It's weighted code 8421. We add a parity bit among them. Then P8421. For 0 it is 000. For even parity, check this. There are no ones means even number of ones 0. Like that. Odd parity BCD ones is 1. There are even odd number of ones in 0, then odd parity of BCD like this. For 1 1001 even parity. For odd parity of 10001. For 2 even parity is 10010. Odd parity 00010. 3 for even parity of 3 0011. Even number of ones 10011. Odd parity odd number of ones. For 4 10100. Even parity 00100. Odd number of ones means odd parity 00101. 5 even parity 10101. 3 number of 3 ones, so it's odd parity 00110. Even parity, that means 2 ones are there, so it is even parity 10110. 3 ones means odd parity 7 10111. It's even parity 4 ones are there, it is in the number of even 00111. Odd parity 8 11000. It is even parity 01000. Odd parity 01001. Even parity 11001. Odd parity. The above table is the parity generation of decimal digits. In general, to obtain an n-bit detecting code, no more than half of the possible two combination of digits can be used. The code words chosen in the such manner that in order to change one valid code word into another word, at least two digits must be complemented. Distance between two code words as the number of digits that must change in one word so that the word results the minimum distance of the code is the smallest number of bits in which any two code offers differs. Clearly, a code is an error detecting code if and only if its minimum distance is 2 or more. If a code has capable of detecting d number of bit errors, it should have the minimum distance of d plus. Error correcting codes. In general, a code is said to be an error correcting if the correct code can always be reduced from erroneous word. In this selection, we shall discuss a single type of error correcting code, known as Hamming code. It is the most popularly used error correcting codes. If the minimum distance of a code is 3, then there a single error changes a valid code into an invalid one, which is distance 1 away from the original code word and a distance 2 from any other valid code word. Therefore, in a code with a minimum distance of 3, any single error is correctable or any double detectable. Similarly, a code whose minimum distance is 4 may be used for either single error correction and double error detection or triple error detection. Clearly, a code has capable of correcting d number of bit errors should have minimum distance of 2d plus 1 means. Similarly, a code has minimum distance means is 4 may be used for either single error correction and double error detection or triple error detection. Clearly, a code has capable of correcting d number of bit errors. It should have the minimum distance of 2d plus 1. If the minimum distance of a code is 3, then any single error changes a valid code word into a valid one, which is a distance 1 away from the original code word and a distance 2 from any other valid word. Therefore, in a code with a minimum distance of 3 and single error is correctable or any double error detected. There is an error correcting code that separates the bit holding the original value from the error correction bits and the differences between the calculated and actual error correction bits in the position of the bit that's wrong. It's called Hamming code. The basic principle is constructing a Hamming error code as follows. To each group of m information or messages, digits k parity checking digits denoted p1, p2 or pk are added to form of an m plus k digit code. Consequently, k must satisfy the inequality 2 power k less than or greater than or equal to m plus k plus 1. In order to be able to specify the checking digits by means of only message digits and independently of each other, they are placed in positions 1, 2, 4, dash dash up to 2k minus 1. Thus, if m is equal to 4 and k is equal to 3, the checking digits are placed in positions 1, 2, 4, while the remaining positions contain the original BCD message bits. Consider for example the message 0100 of decimal 4. P1 is selected as so as to establish even parity in positions of 1, 3, 5, 7. P2 is selected as to be established even parity in position of 2, 3, 5, 6, 7. P3 is selected so as to establish even parity in position 4, 5, 6, 7. Originally, BCD message parity check in positions of 1, 3, 5, 7 requires P1 is equals to 0. So we check that even parity. So we check all the positions of 1, 3, 5, 7. The missing digit P1 we are following even parity. So we fill the one as would satisfy the even parity. Same like that. Parity check positions of 2, 3, 6, 7. It requires P2 is equals to 1. It satisfies then even parity. Parity check position 4, 5, 6, 7 requires P3 is equals to 1. So it satisfies the position even parity. The error locations and corrections is performed in the following manner. Suppose for example the sequence of 0, 1, 0, 1, 0, 1 is transmitted, but due to an error in the fifth position, the sequence 0, 1, 1, 1, 0, 1, 0 is received. Same, by checking the positions of the P1, P2, P3, P4, we get, first we check the 1, 3, 5, 7 parity check, then we get P1. If it satisfies the even parity, then next go to second by keeping C is equal to 0 only. If it is any wrong or it does not satisfy the even parity, so C 2 power 0 plus 1, position we are checking is 0, so 2 power 0 plus 0 is equals to 1. 2, 3, 6, 7. We check the positions of 2, 3, 6, 7. If it satisfies the even parity, then we move to next, but it does not satisfy the even parity, so it satisfies the even parity, so we move to next. C is equals to 1. We do not change it. 4, 5, 6, 7 parity check. 0, 1, 1, 1, 0. Here the parity is not satisfied. So it is in the power of 2 power 2. It means 4. 1 plus 4, 5. We have checked all the positions. Then C is equals to 5. Then we have to keep that the position at the 5 have an error. Thus the position number of the error in the position 5. To correct the error, the digit in position 5 is complemented and the correct message 0101010 is obtained. At position which the code is wrong, we should do complement of it. If it is 0, we do 1. 1 if we do 0. The original message 0100 is obtained by removing the parity bits. Thanking you for giving me this opportunity.